Hi friends, earlier we were discussing limits rather informally. We are doing an informal definition that if x is approaching x naught and if f of x is approaching some number l, then l is the limit. But this is slightly informal, right? Approaching is slightly dicey. It is not very concrete statement. Someone will say something is approaching something, it is close enough, or it is close enough, f of x is close enough to L or not close enough. These are all not so clear statements. So let us attempt a formal definition of limit, which is more precise mathematically. Right. We say limit of f of x as x approaches L naught is the number L. Let's say there is some limit. Okay, we write it like this. If for every epsilon greater than 0, for every epsilon. Epsilon can be 1, it can be 2, it can be zero point 0.1, it can be 0.001, whatever. Whatever epsilon you take greater than 0, just however small, however big, there exists a corresponding delta, which is again greater than 0, such that for all x, this delta is present, whichever epsilon that you are taking, there will always be some delta. Okay. And what is this delta? This delta is such that x minus x naught. Absolute value of this is lying between 0 and delta, and when this is lying like this, what does that mean? The value of the function minus L is always lesser than epsilon. Okay, this is little tricky. Let us try to understand. Okay, so now let us take this example. Let us take one example. Okay, we are saying, let's say the graph of function is something. We are saying this function is approaching L. Okay, the limit of this function is actually equal to L. Let's say some function. Okay, limit is L. Now someone says my epsilon is some point one. Okay, some point one. Let's say some L is this L is some number called 5. Okay, L is some number 5 and epsilon is point one. What does that mean? The value of this function should lie between 5 minus point one, which is 4.9, to 5.1. Okay, so what does that mean? If epsilon, see, f of x minus L, absolute value of this should be less than epsilon. If epsilon is zero point 0.1 and this L is f of x minus L, absolute value of this should be less than epsilon. Okay, if epsilon is zero point 0.1, what does that mean? F of x minus L. So L is constant, L is fixed. L is, let's say we have defined L as 5. Okay, now this is an absolute value. F of x can be greater than L, f of x can be lesser than L. So f of x can be here or can be here. Doesn't matter. But absolute value of the difference should be less than epsilon. So that means f of x can lie anywhere between this part. Okay. If we define this is the point L, this point, and this point is L plus epsilon, this point is L minus epsilon. Absolute value of f of x minus L should lie less than epsilon means, right? F of x could be higher than L, f of x could be lesser than L, but f of x should lie in this range. F of x should lie in the range of 4.9 to 5.1. This is 4.9 and this is 5.1. Okay, this should lie in this range whenever x minus x naught is lying in this range, 0 and delta, and we have to find some delta. Okay, so what does that mean? Some delta. Okay, now again let's say the delta is again 0.1, x0 is 4, let's say, and x minus delta, which is delta is, if you say delta is 0.1, then this is 3.9 and this is 4.1. Okay, what does that mean? As long as x is lying between 3.9 and 4.1, x is between 3.9 and 4.1. Okay, then f of x should lie between 4.9 and 5.1. Okay, this is the statement. The statement is here, please read the statement. X minus x naught epsilon should lie between 0 and delta, then f of x minus L should lie between epsilon. Okay, so here f of x is defined on an open interval about x naught except possibly at x naught itself. Okay, so this f of x need not be defined at x naught. So that's why we are not concerned about x naught. F of x naught we are not saying. As long, except at x naught, what we are saying, this one, f of x minus L should lie less than epsilon. Okay, at x naught, we are calling the value as L. Okay, f of x naught is not defined, firstly, is not defined. Okay, so we are saying, because it is not defined, at x naught we can take this value L. If at x naught we can take this value L if for all x between this range 3.9 to 4.1, that is within the range of x minus delta to x plus delta. Okay, f of x will lie in this range. F of x will lie in this range of 4.9 to 5.1, and then we'll agree that this 5 is a limit of this function. Okay, now there should be some delta for whatever epsilon that you are taking. Here in this case, someone picked zero point 0.1. Someone might pick 0.01. Okay. So then this becomes 5.012. Right. The upper limit and lower limit will become even smaller. Then you should have some other delta. Okay. You should have some other delta where within this range, the value of function is always lying between 5 plus 0.01 and 5 minus 0.01. Let us take one example. Okay. Let us take this function x squared minus 1 by x minus 1, which is nothing but x minus 1 into x plus 1 by x minus 1, which is equal to x plus 1 as long as x is not equal to 1. Right. For all other cases, this function is equal to x plus 1, but only when x equal to 1. Sorry, the graph I have drawn is slightly different. Let us take another case. That is x square plus x by x, which is nothing but x into x plus 1 by x. This is equal to, forget about this one, x squared plus x by x. This function is equal to this. This is equal to x plus 1 as long as x is not equal to 0. Right. X is not equal to 0, then we can cancel x and x. Okay, when x equal to 0, this is not defined. So there is a hole here. Okay, this is equal to graph of this function x plus 1. As long as x is not equal to 0, when x is equal to 0, there is a hole here. Now, what is the limit of this function? Let's take the formal definition. Limit x tends to 0. Okay. Limit if we take as 1. Okay. If we take limit as 1, what does that mean as per this definition? 1, if you are taking this epsilon, if I are taking the epsilon as 0.1. Okay. 1 plus 0.1 to 1 minus 0.1. So that is 1 plus 0.1 to 1 minus 0.1. Okay. We are defining this range. Okay. This is the range the graph should lie when, so when epsilon is defined as 0.1, there should be a delta. In this case, what is the delta? The delta is again 0.1. Okay. 0.1, 0 plus 0.1 to 0 minus 0.1, when it is lying like this, right? Between this range of delta, minus 0.1 to plus 0.1. This graph is entirely lying, this part of this graph, right? This graph is entirely lying between these two lines. What are these two lines? What are these two horizontal lines? The horizontal lines are 1 plus epsilon, 1 minus epsilon. Okay. So when someone defined an epsilon, let's say someone defined as epsilon as 0.2. Okay. That is 1 plus zero point 0.2 to 1 minus zero point 0.2. Okay, the graph should lie between this line and this line, 0.8 to 1.2. If that is the case, is there a delta? Yes, there is a delta. What is the delta? The delta is given by this range, right? By this one. This is again 0.2. The delta is again, if epsilon is 0.2, delta is also 0.2 in this case because this is a straight line. So as long as x is lying between 0 plus zero point 0.2 and 0 minus zero point 0.2. Y will always lie between 1 plus zero point 0.2 and 1 minus zero point 0.2. So that's why we can call 1 as the limit. Now let's say someone else said, okay, the limit is not 1. the limit is, let's say, 1.2. Someone defined 1.2. Now 1.2, let's say I say 1.2 is the limit. Then what will you say? You will say, okay, my epsilon is again 0.1. Okay, so then you will say my epsilon is 0.1. So if your limit is 1.2, if you are claiming, then the graph should lie between 1.1 and 1.2, should entirely lie between 1.1 and 1.3, right? 1.2 minus epsilon, 1.2 minus zero point 0.1 versus 1.2 plus zero point 0.1. So the graph should always lie between 1.1 and 1.3. You'll ask me, tell me the delta. Tell me the delta, that is x. Tell me the range of x in which this graph is always lying between 1.1 and 1.3. Now I am clueless, right? Because there is no such delta. Whatever delta, if I take the delta is big or small, it doesn't matter, right? This graph is should always lie between this range. It is not lying this range. Let's say I take delta as this from here to here, from here to here, right? But then what is the graph? The graph is ranging between minus 0.6. So this is 1.62. This is 0.62, probably 1.4. This graph is ranging. What is the range of this graph? This point and probably some this point. This graph is ranging between 0.6 and 1.4. If I take a big delta, if I take a small delta also, then also it doesn't matter, right? So let's say I take a small delta as again zero point 0.1. Okay, let's say I take a small delta as 0.1. 0 plus zero point 0.1, 0 minus zero point 0.1. So where is the graph lying between? The graph is lying between 0.9 and 1.1. Okay, if I take a small delta, then this graph is lying in this range from here to here, 0.9 to 1.1. So whatever I do, I cannot find a delta. I cannot find a range of x around 0, right? I cannot find x plus x minus delta and x plus delta such that this graph is entirely lying in this range, in this range, right? It is not possible. It is only possible when I pick the limit as 1. If I don't pick limit as 1, it is clearly impossible for me to pick a delta such that whatever epsilon that you are giving, my graph will lie in that range. So, for example, if I pick 1, then you give whatever epsilon. You'll say the graph should lie between 1.1 and zero point 0.9, and I'll say, okay, this is the range. So your epsilon, your delta should lie between uh, delta delta is zero point 0.1 and x should lie between zero point 0.9 and 1.1. So basically around 1, around limit. Okay, so let's come to the different definition of the limit. If there is a limit, then around the limit, above or below, if the value of the function is lying less than epsilon, for every epsilon, epsilon can be as small as possible. Okay, for every epsilon, even if it is 0.1, 0.9, whatever, there should always exist some delta such that the within this delta, within the range from around x naught, within that delta, if we say this is x naught within the delta, so x should lie between um, plus or minus delta of the x naught. Okay, then as long as this is lying like this, the value of the function should lie within epsilon units of the limit. Okay, so and this should exist for all epsilon, right? Let us take another example. Let us take this example. This example is sine 1 by x. Okay, sine 1 by x, the limit does not exist. Okay, so sine 1 by x, the graph looks like this, because when x becomes very small, when x tends to 0, 1 by x will tend to infinity, and this will fluctuate a lot. So the sine 1 by x, as x is coming closer to 0, it will fluctuate a lot. Now let's say I say that the limit of this function, limit of this is some 0. Let's say I claim the limit is 0. Then what will you tell? Okay, tell me the range of x. Tell me a delta. You will say, first you will tell me epsilon, my epsilon is 0.5. Okay. Then you will claim you're giving me a challenge. The challenge is your epsilon is 0.5. Now give me delta where the function is always lying between 0.5 and minus 0.5. Okay. that is 0 plus 0.5, because I am claiming the limit is this. Then you will say, give me that delta where the function is always lying between this range and this range. Okay, the function is always lying. Now I cannot take any range, right? I cannot take any delta, because whatever small delta I pick, see if I pick this delta, if I pick this delta, right? So then if I pick this delta, this what this function is going beyond zero point 0.5, right? The function is always going up to 1. Whatever small I pick, there will always be some function, some part of the function which is going beyond zero point 0.5 and which is going lesser than zero point 0.5 also. There is no way I can create this box, right? This box where the entire function is actually lying between this range, between plus zero point 0.5 and minus zero point 0.5, whatever delta that I take, whatever small delta I take. Okay, if I take this delta, f of x, when x is lesser than this delta, so when x is lying between these two places, the value of the function should lie between these two lines. But here, whatever delta that you take, the value of the function is always going to 1 and minus 1. So there is no delta that can be taken such that to restrict the value of this function between this point and this point. So limit does not exist when x equal to 0. For example, if it is some point like this, some point like this, then then I can always, so if you say then the value of the function should always lie between this point and this point, then I can always claim, okay, this is my delta. My delta is, you restrict between these 2 points, your function is always lying between these 2 points then, right? Your function, sorry, your function will always lie between these 2 points. Okay, if you are given my function should always lie between these 2 points, then what will I say? I will say this is my delta. This is my delta. Okay, so I'll extend it a little bit. I'll extend this. I'll say this is my delta. Between this delta, your function will always lie between this line and this line, as long as your x is there between this and this. Right. So in this case, you can always choose some delta. For example, delta can be like this. This part of this delta, if you define this delta, then between here and here, let's say if my x naught is here, then between these 2 points, the graph of function is this, right? Till this point. Okay, the graph of function is till this point, which is always lying between these 2 points. These 2 points are given to us, which is always lying between these 2 points. So as here, because there is no fluctuation, we can always define deltas to ensure the graph of function is always lying between two different between epsilon within the limit of um, f of within epsilon of that limit, right? So basically, what does that mean? F of x minus L should be less than epsilon. Okay, absolute value of this. Okay, let us take this example. Show by example that the statement is wrong. The number L is the limit of f of x as x approaches L naught. If f of x gets closer to L as x approaches x naught. This seems correct, right? The statement seems normal only. L is the limit as x approaches x naught. If f of x gets closer to L. Okay, but see, the important thing is we have to be very precise. Okay, let's take a graph like this. Let's take a graph like this, y equal to x square. Y equal to x square. F of x as x approaches x naught, as x approaches x naught is 0, f of x is approaching L. That's what we are saying. So now, so this function as x approaches x naught, we can say it is approaching towards minus 1 also. What is it restricting? This function should lie as close as we want to minus 1. Right. Here the statement is not saying that. Whereas our definition says f of x minus L, absolute value of this, should be less than epsilon, whatever small value is this. Here it is just saying the function is approaching minus 1, but it is not saying the function approaches minus 1 to as close as we want. Right, that piece is missing here. F of x is getting closer to L. F of x is definitely getting closer to minus 1 here. Right. Here, the distance between this function and minus 1 is actually reducing, is always. But it doesn't mean that the distance is as small as we want. Right. Here, what is the definition? When x minus x naught should be less than delta. Right. So here the problem is, when someone defines it should be less than something, then we don't have a delta here. Right. If it should be as close as you want, and then the function should lie within this range of this delta. When we define this delta, when we define some delta, the value of this function should always lie within this epsilon. Whatever epsilon that you have given, then if we should be able to define a delta within which value of the function should lie within that epsilon range. So that's why this is wrong. Okay. Let's take another example. Limit L is the limit of f of x as x approaches x naught. X approaching x naught. If given any epsilon greater than 0, any epsilon greater than 0. So for all epsilons, there exists a x such that f of x minus L is less than epsilon. So what it is saying, here also the definition is almost close, but something is missing. We need to be very careful. Here, for all epsilons, however small, there exists some x for which f of x minus L is less than epsilon. But what is the thing that is missing here? It is not just one x. What we want? All x's within the range of uh, within the range of x naught plus delta and x naught minus delta. Right? Not just one x. We want all x which is lying between x naught minus delta and x naught plus delta. For all this x, f of x minus L should be less than epsilon. Here, that part is missing. Right here, it is not saying what happens to the remaining x's. Right here, it is talking about there is one x which is lying within this range, which is satisfying this condition. For example, our sine 1 by x curve. Here it is saying, what does that mean? Here it is saying there is, in this case also, there will always be some x. So for example, if I define my epsilon is like this, whatever epsilon is like this. Here, what is this condition saying? This condition is saying there is some x for which f of x minus L is less than epsilon s. Here also there are a lot of x's. So this point is lesser, this point is lesser, this point is lesser, this point is lesser. So there are a lot of x, lot of values of x for which f of x minus L is within this range. But the point is, we need not just one or two x values of x. We need all values of x within a range for which f of x is always lying between these two horizontal lines. Within two values of x around this x naught that we are saying, the value of function should always lie between limit plus epsilon and limit minus epsilon. Here it is not saying that. Here there is one value of x for which this number f of x is close to very close to L. This is saying that. This is saying this function is coming very close to this limit at least once. No, that's not what we want. This function is continuously getting close, and in fact it is always closer. Is the distance between function and limit is always lesser than epsilon as long as x is lying within the limit of delta, within delta of x naught. Right, within delta of x naught, if it is there, then the function should always be lesser. For all values of x, it should be lesser, not just one value of x. That's why this statement is wrong. So it is important for us to be very particular about what statements that we are making. So naturally, this is the precise definition of limit. So that's why this is little complex to comprehend. But it is good to know the precise definition of limit to understand the beauty of calculus and these functions, right? Limits. So this is the limit, but generally we use the informal way where the function is coming very close to L. Then we'll say that that is the limit from both sides of L, from both sides of x naught. If the function is approaching L, we'll say this. But the precise definition is very, very important also, because whether limit exists or not. For example, in this case, sine 1 by x, we need to know how exactly does it behave. We need to be able to prove formally also, because by looking at the graph we can clearly say that limit exists or not, but the graphical representation is always not so easy. That's why it's important for us to know the formal definition and appreciate it also, and appreciate the formal definition, right guys, to have better conceptual understanding also. So please see these statements, they are so close but still they are so far from the truth, right? The definition is almost very enticing that to accept in these two cases, but we should be very careful in such statements, right guys? Hope you like this. Thank you.